Okay, this is a pretty straightforward example. Is 27 a factor of 144? Now remember, always use the framework, which means we pull out a big number, we pull out a small number, and we compare the DNA. In this case, pretty obvious what the big number and the small number is. Big number is 144, small number is 27. If we were dealing with more complicated numbers and it wasn't quite as obvious, notice that they tell you that 27 is the small number because they call it a factor. Okay, so what we're really being asked is, does 144 contain all of the DNA of 27? Or if you want to put that in math, is 144 over 27 an integer? Okay, well, let's break down our numbers. 144's DNA is 2 times 2 times 2 times 2 times 3 times 3, which is 2 to the 4th times 3 squared. 27's DNA is 3 times 3 times 3, which is 3 cubed. So, does 144 contain all the DNA of 27? No, we're missing a 3. It does not. Let's change the question just a little bit. And is 27 a factor of 144 times 21? Now remember, when we multiply numbers together, all we do is combine their DNA. So the DNA of 144 times 21 must be 2 to the 4th times 3 squared times 3 times 7, because that is the DNA of 21. And all we do is tack it on to the DNA of 144. Now, does 144 times 21 contain all the DNA of 27? Yeah, it sure does. We picked up that other 3 that we needed. Okay, good job. What is the largest positive integer value for k, in which 7 to the k divides into 147 to the 15th? Not exactly sure what's going on here, but we see the magic word divides, and that tells us get everything's DNA. So let's take a look at the DNA of 147. What does that break down to? 3 times 7 squared. And by the way, if you're wondering, like, can I break down the DNA quickly? Yeah, there's some tricks. There are some tricks to understand whether a big number like 147 can be divisible by numbers 2 through 12. Now, I go through those rules in the companion guide. It's at the back of the companion guide. It is critical that you memorize those rules, and not only is it critical, dead useful on the test. So make sure to look at those. So the DNA of 147 is 3 times 7 squared, and that means that the DNA of 147 to the 15th must be, well, if 147 has 1 3 in it, then 147 to the 15th must have 15 3s in it. And if 147 has 2 7s in it, then 147 to the 15th must have 30 7s in it. Okay, and then what about the DNA of 7 to the k? Well, that's just a bunch of 7s multiplied together, and we don't know how many 7s are multiplied together because we don't know what k is. All right, so what we're really being asked is, how big can we make k so that 147 to the 15th divided by 7 to the k is still an integer? So basically we're being asked, how many 7s are there in 147 to the 15th? Well, there are 30 7s. That means the biggest number that we can make k is 30. Is it possible that k is 7? Yeah, it's just not the biggest number that we can make k. Is it possible that k is 31? No, it's not. Because remember, the big number has to contain all the DNA of the small number, and the big number only has 30 7s in it. All right, nice job. Let's take a look at another one. If x is divisible by both 18 and 49, is x over 294 an integer? Okay, how are we going to do this one quickly? We're going to pull out the big number, we're going to pull out the small number, and we are going to compare DNA. So the big number, x. Small number, 294. Remember, numerators are always the big number, denominators are always the small number. Okay, So the question we're being asked is, does X contain all of the DNA of 294? Or if we want to put that in math, is X over 294 an integer? Okay, well, let's break down what we're told. We are told X is divisible by 18, and we're also told that X is divisible by 49. What does that mean? Well, if X is divisible by 18, or in math, X over 18 is an integer, that must mean that X contains all of the DNA of 18. So X must contain 2 times 3 squared. Hey, by the way, is it possible that X contains a heck of a lot more DNA than just 2 times 3 squared? Yeah, X could be an enormous number. We don't know, but we know for sure that X contains 2 times 3 squared. Now, we're also told that X is divisible by 49, which of course means X over 49 is an integer. So we also know that X contains all of the DNA of 49, so X must contain 2 7s. Now, again, could X contain a heck of a lot more DNA than just 7 squared? Yeah, X could be, again, an enormous number, but it must contain 7 squared. And if we combine that information, we know for sure that X, at a minimum, must contain 1 2, a couple of 3s, and a couple of 7s. And once again, to drive the point home, could X contain a lot more DNA than that? Yeah, you bet it could. But it must contain the 2 3s, and the 2 7s. Okay, so now that we know what the DNA of the big number is, let's take a look at the small number, which is 294. And if we break that down, 294 is 2 times 3 times 7 squared. So the question is, does X contain all of the DNA of 294? Yeah, it does. X is the big number and contains all of the DNA of 294. Nice job. If X is prime, what must be true of X times X plus 1 times X plus 2 times X plus 3? Well, how are we going to approach this one? Well, the very first thing to recognize is this X plus 1, X plus 2, X plus 3 business. All that means is those are consecutive numbers, like 3, 4, 5, 6, or 7, 8, 9, 10, something like that. X plus 1, X plus 2, X plus 3 is how we write consecutive numbers in math. And by the way, if they would have given you like X plus 2, X plus 4, those are also consecutive numbers. You're just counting up by 2s, or X plus 3, X plus 6, also consecutive numbers. You're just counting up by 3s. In this case, we're given 4 consecutive numbers, and we're just counting up by 1s. All right, so now that we know that, what the heck are we being asked? Well, they want us to evaluate this kind of string of 4 consecutive numbers and figure out if it's divisible by 24, if it's a perfect square, and if X plus 1 times X plus 2 is even. Well, I think we can do that, and I think we can learn a heck of a lot of really, really good stuff along the way. So let's take the very first one. So does X times X plus 1 times X plus 2 times X plus 3 contain all the DNA of 24? So does our string of 4 consecutive numbers contain all the DNA of 24? And remember, when you multiply numbers together, we just combine their DNA. All right, well, let's not take a look at all 4 numbers at first, because that seems intimidating. Let's just take a look at X and X plus 1. Well, those are 2 consecutive numbers. Now, let me ask you a question. Is one of those numbers, X plus 1, is one of those numbers even? Yeah, it has to be. There is simply no way to write down 2 consecutive numbers and not have one of those numbers even, like 1 or 2 or 3 or 4 or 9 or 10. One of those numbers must be even, so that means one of the numbers in our 4 consecutive numbers is even and must contribute a 2 to the DNA. Which number is even? We don't know. We don't know, but one of them must be. Okay, well, let's expand our analysis just a little bit. And let's take a look at X, X plus 1, and X plus 2. Now, those are 3 consecutive numbers. So let me ask you a question about 3 consecutive numbers. Will one of those numbers, X plus 1, X plus 2, will one of those numbers be a multiple of 3? Absolutely, it has to be. There is simply no way to write down 3 consecutive numbers and not have one of those numbers be a multiple of 3, like 1, 2, 3, or 7, 8, 9, or 20, 21, 22. So that means that one of our numbers in our 4 consecutive numbers must contribute a 3 to the DNA. Do we know which of the numbers does that? No, we don't, but one of those numbers must. Okay, now let's take a look at the entire string. X plus 1, x plus 2, x plus 3. Now those are 4 consecutive numbers. Now will one of those numbers be a multiple of 4? Absolutely, it has to be. There is no way to write down 4 consecutive numbers and not have one of those numbers be divisible by 4. 1, 2, 3, 4, starting 9, 10, 11, or 12, or 19, 20, 21, 22. That means one of our numbers in our string of 4 consecutive numbers must contribute a 4 or a 2 squared to the DNA. Do we know which number does it? No, we don't, but we know that one of them must. So we know that at a minimum, the DNA that is in our sequence of 4 consecutive numbers, it is going to have a 2 in it, it's going to have a 3 in it, and it's going to have a 2 squared in it. For sure. Could it have a lot more DNA in it? Yeah, you bet it could. It could be a huge number. But it has to have 3 2s and a 3 in it. All right, now we're being asked, is our string of 4 consecutive numbers, when we multiply those numbers together, is that divisible by 24? Our string of 4 numbers is the big number. 24 is the small number. So what's 24's DNA? Let's see. 24's DNA is 2 cubed times 3. The big number, our set of 4 consecutive numbers, contains all the DNA of 24. So will those 4 consecutive numbers, when they are multiplied together, be divisible by 24? Yes, absolutely. Okay, good job. Let's take a look at number 2, which is this business about, are these 4 consecutive numbers a perfect square? Now let's think about this a second. All we have to do is come up with one example where these 4 consecutive numbers multiplied together is not a perfect square, and then we can say for sure that number 2, no, it's not. Let's see if we can find an example. Well, let's see, 2 times 3 times 4 times 5, I think that's 120, and guess what? 120 is not a perfect square. So are those 4 consecutive numbers a perfect square? Well, they don't have to be. Let's take a look at number 3. So number 3 says, is x plus 1 times x plus 2 even? Now in math, that is x plus 1 times x plus 2 divided by 2, an integer, or if you want to think about it in our framework, does x plus 1 times x plus 2 contain a 2 in its DNA? And we kind of already covered this ground when we evaluated that first statement. Yeah, x plus 1 and x plus 2 are 2 consecutive numbers. One of those numbers must be even. Again, we don't know which one, but one of those must be an even number. So when you divide it by 2, it will give you an integer. Okay, this one is tricky. There's a lot of really, really good stuff in this one, a lot of good number properties stuff, and this idea of being able to evaluate consecutive numbers definitely comes up on the higher levels in the test. All right, nice job.